All right, just to give you a brief recap of what was discussed. So the motivation behind this work is that the current approach to designing secure wireless protocols is like a performance first, security second kind of mentality. And we have basically an arms race between trying to uncover attacks or discover attacks against protocols and developing patches to defend against those attacks. And at no point in the process can we say definitively that this particular protocol is secure against all attacks. So there's a need for a theory to provide more direction to the process of designing secure wireless protocols, to give more insight into this problem. And we need to know whether there are fundamental limits on what can and can't be done. And when we talk about security, we're talking about security in the sense of having a functional, reliable network, not only in the sense of preserving secrecy or privacy, as you know, we traditionally understand in the information theory community. So I'm going to just give you a bit of background on some terms that will come in, that I'll be referring to or referencing later on in the talk. So first, Professor Kumar talked about a network utility function. And what we mean is in a network, you have a bunch of source-destination pairs. And each of those source-destination pairs communicates at a certain throughput. And the network utility function measures the utility that's derived by the network from that throughput vector. And we evaluate the utility over all pairs of nodes that are cooperating. So if we have a network that has attackers or hostile nodes, some of them might not cooperate, but we evaluate the utility function over all cooperating pairs of nodes. And the other term that we're going to be referencing is a concurrent transmission set. And very simply, that's just a set of nodes that simultaneously transmits at a certain rate vector. Okay. So here's the first, I guess, fundamental limit that we're going to encounter. Now, say I have a utility function, like any utility function. An upper bound on the utility that can be achieved by a network, by any protocol, is this expression here, this min-max. And why is this an upper bound? Okay, first maybe I should say what this expression means. What this means is that first, every bad node announces a priori whether it's going to, what it's going to do, whether it's going to jam or cooperate with the protocol. It announces that beforehand. And then, given that information, the network chooses a protocol to maximize utility. And the bad nodes attempt to post facto minimize the utility. So why is this an upper bound? Well, first of all, the good nodes in the network know a priori what everyone else is going to do. And in practice, this is not true. In practice, you announce the protocol first, and then if there are bad nodes in the network, they choose their action to minimize utility. So we have like a reversal of the usual approach. The second reason is that the bad nodes only have two options. They can either jam or they can cooperate with the protocol. But we know that a group of colluding bad nodes is capable of much more complex and sophisticated attacks. But here we're saying that they only have two options. They can either jam or cooperate. And moreover, it's impossible to stop a bad node from doing one of those two options. You can't have a protocol that stops a bad node from jamming. You can always choose to jam, And similarly, you can't have a protocol that stops a bad node from cooperating, because a bad node that cooperates with the protocol is indistinguishable from a good node. And the third reason why this is an upper bound is that this rate vector here, this utility is maximized over all the rate vectors in the information theoretic capacity region, which is unknown. That's what we mean by all protocols. So we have this upper bound on the utility that can be achieved for any utility function and by any protocol. Okay, so I'm going to give you a more modest upper bound where instead of maximizing the utility over the information theoretic capacity region, I'm just going to look at protocols that time share over concurrent transmission sets to make the problem a little more tractable. And the utility that's achieved by our protocol is this expression right here. So if we compare, it's similar, except here each bad node either jams and or cooperates in a concurrent transmission set. So we have some extra stuff. In basically, where the activity of a bad node can change in different concurrent transmission sets. So if I compare this lower bound and the upper bound, we have some similarities that are kind of encouraging. So one similarity is that we have this min-max formulation, which basically means that in effect, the good nodes know what the bad nodes will be doing a priori, in effect. And also, all of the actions of the bad nodes are basically limited to jamming or cooperating with the protocol. And this result applies for all continuous utility functions. But there's some differences, and that's one is, as I mentioned before, the behavior of the bad node is specific to a concurrent transmission set. So in a different concurrent transmission set, in one concurrent transmission set, a bad node may choose to cooperate. In another, it may choose to jam. And in addition, we have a bad node can also simultaneously jam and cooperate in a concurrent transmission set. So this lower bound doesn't exactly match the upper bound, but it's close. And I think it has some implications that are, interesting to people who design secure wireless protocols. So what it means is that obviously you have a protocol that forms a fully functioning network from a collection of good and bad nodes. But it also implies that the network achieves this utility regardless of what attacks are mounted against it by bad nodes in the network. All attacks. And moreover, attacks are basically effectively limited to just jamming and or cooperating. And as I mentioned earlier, it's impossible to stop a bad node from jamming or cooperating. And we have this min-max formulation where the bad nodes, in effect, are gaining no advantage by knowing the protocol beforehand. And so this is, I guess, my favorite. And we have an achievable utility that has the flavor of optimality. So when I was a master's student, I worked a lot on the relay channel, and depending on whether you'd used decode forward or compress forward, you had something that looked like that was close to the converse, but not quite. And so we have something kind of similar here. Okay, so I'm going to walk through the protocol for a very simple example. And here's some questions that I'd like you to keep in mind to help convey the main ideas more effectively. So how can we say that the protocol is immune to all attacks without knowing what all of the attacks are? So we haven't even characterized the list of all possible attacks. And maybe it's a huge list. Maybe it can't even be characterized. But I'm claiming that the protocol is immune to all of those attacks without even describing them first. And moreover, why can I say that all the attacks are basically limited to either jamming or cooperating? In practice, denial of service attacks can be very complex, very sophisticated, but I'm making this statement here. And keep in mind that the network doesn't know a priori which nodes are good and bad. So, you can have situations in which bad nodes decide to cooperate initially, but then later choose to not cooperate. So what happens in cases like that? And how can I even talk about the utility of a network when I don't know which nodes are good or bad? Like which nodes do I care about? I don't know which nodes are good or bad. Do I care about whether the bad nodes do I incorporate the bad nodes into the utility function? And moreover, the nodes that are cooperating with the protocol might be changing. So as I said before, a bad node might cooperate, and then it might choose not to cooperate. So how do I evaluate the utility function in this context? So at the end of the talk, if you have satisfactory answers to these questions, then my work is done. Okay, so I'm going to introduce a very simple 3-node network and walk you through the protocol as it operates on this simple 3-node network. Okay, so we have 2 good nodes, node A and B, and node C is a bad node. And obviously node A and B don't know that node C is bad. Node C knows that A and B are good. There are just 2 modulation schemes at 1 bit and 2 bits per second. And and node A and B can communicate. So when node C does not jam, the communication rate between A and B is 1 bit per second. But sorry, did I say that right? When C jams, the communication rate between A and B is 1 bit per second. But if C doesn't jam, then the communication rate is 2 bits per second. And we have this, and we're going to use a simple utility function, which is basically the minimum rate over all the pairs that are cooperating. So this is the example network that I'm going to walk the protocol through. And here I have here is a state diagram of the protocol. There's 5 phases: a neighbor discovery phase, a network discovery phase, a scheduling phase, a data transfer phase, and a verification phase. And the protocol cycles repeatedly through these last 3 phases. Okay, so we start with a primordial birth. So at some point, node A, B, and C, they all turn on. And we can assume that they simultaneously turn on. I've also looked at the case where the primordial birth, where the birth times are unbounded, and it's interesting but a lot more complicated. So in the neighbor discovery phase, basically the nodes try to take a tentative step towards forming a network. They try to learn who their neighbors are. They try to learn the clock parameters of their neighbors. And at the end of the neighbor discovery phase, node A will know that its neighbors are node B and C, and node B will know that its neighbors are A and C. And we're assuming that node C, though bad, is cooperating because otherwise it's not very interesting. And also keep in mind that node A and B are not synchronized, but yet they have to communicate with each other. So we need like a sort of a mechanism that allows these nodes to cooperate and or to communicate with each other, even though they may encounter collisions, packet collisions, and so forth. Okay, so in the network discovery phase, node A and B tried to come to a common view of the network topology. So they share their lists of neighbors. They exchange lists of neighbors with each other and infer a network topology. And the key idea here is that they have to have the same view of the network topology. They can't have different views. So in a three-node network, this problem is kind of simple because node A and B are able to directly communicate. But in more complicated networks, you need to use a Byzantine generals algorithm to ensure that the good nodes have a common view of the topology. And having a common view is also not enough. There might be network-wide inconsistencies as well, so that requires some more work, a consistency check. I'm not going to go into the details of this, but I'm just sort of letting you know that all of these mechanisms are necessary. Okay. And so now we're getting into the scheduling phase. Now, there are 6 possible feasible concurrent transmission sets. So node A and B can talk at 2 bits, or they can talk at 1 bit. Node A and C can communicate at 2 bits or 1 bit, and similarly, node B and C can communicate at 2 bits or at 1 bit. And each node attempts to solve this expression. So basically, what they're trying to do is find a schedule in which the utility is maximized. And the utility we're using is this the minimum over the minimum throughput over pairs of nodes that cooperate. And so the solution to this, and initially we're assuming that all nodes are cooperating. So our initial assumption is that all nodes are, the initial assumption of each node is that everyone else is cooperating. And so the solution is that each link communicates at a rate of 2/3. Why is this? Well, they start at 2 bits per second. They start using the link at 2 bits per second, and they each get an equal share. I hope this is clear. Okay. And so in the data transfer phase, the nodes try to execute this schedule. And so here's where things, I guess, get a little bit interesting. So when node A and B try to communicate at 2 bits per second, the bad node jams. And this concurrent transmission set fails. So what that means is that some packets don't successfully make it from node A to B. But in the other two concurrent transmission sets, node C cooperates. So node A and C are able to successfully communicate. Node B and C are able to successfully communicate at 2 bits per second. It's only in this concurrent transmission set that node C decides to jam. So what node A and B do is when a packet doesn't arrive, a scheduled packet doesn't arrive, they just take note of it. They keep note of it. And in the verification phase, they share with each other the packets that have failed to arrive. And so this concurrent transmission set gets identified as having failed. And it's removed from the set of feasible concurrent transmission sets. And so basically, the minimum rate over that first round is 0 bits per second. So it was not a good round. And the protocol cycles back again for round 2 and goes back to the scheduling phase. And now when we solve this, utility maximization problem, we have a smaller set of feasible concurrent transmission sets over which to choose from. And we assume, and we continue to assume that if a node is represented in the feasible concurrent transmission set, then it's presumed to cooperate. Sorry, yes? Right. So one of the assumptions of the model is that the subgraph of good nodes is connected at some base rate. So they exchange that information over that base rate. Okay. And so, so the solution to this new problem, the solution to this problem with now a smaller set of feasible concurrent transmission sets is 1/2. So node A and B now are communicating at 1 bit per second, but they get half the time. Node B and C communicate at 2 bits per second. They get a quarter of the time. And similarly, node A and C communicate at 2 bits per second, but they get a quarter of the time. So in the so we go through the data transfer phase again. And so here, node C continues to jam while node A and B try to communicate. But since they're communicating at 1 bit per second, the packets are successfully received. And but then node C decides not to cooperate with either of these concurrent transmission sets, and they fail. So basically, packets that are intended to travel from node A to C or C to A, they don't arrive. And so once again, node A and B, they keep note of what scheduled packets failed to arrive. And in the verification phase, those concurrent transmission sets are added to the set of failed concurrent transmission sets. Okay, so here I'm going to refer back to the first question I asked, and that is, how do we avoid having to preemptively identify every possible attack? Why can I claim that it's not necessary for me to give you a complete list of all possible attacks? Why can I say the protocol is immune to all possible attacks without giving a list, without describing this list of them to you beforehand? And basically, the main idea is that an attack either disables a concurrent transmission set or it doesn't. It can have one of 2 possible outcomes. And so although the list of possible attacks might be infinite, you can't characterize it perhaps, but its effect is finite because there's only a finite number of concurrent transmission sets. And attacks and concurrent transmission sets that are disabled by an attack are pruned. We never use them again. And there's only a finite number of them. So, and an attack that disables a concurrent transmission set is basically equivalent to jamming. So I guess that's the answer. The answer to that question is that we look at the effect of the attack, not at the specific mechanics of the attack. We look at its effect, and its effect is it either disables a concurrent transmission set or it doesn't. And so, so the minimum rate over the second round is still 0 bits per second. So we're not doing very good. And so we go again through the scheduling phase, now we have a much smaller set of feasible concurrent transmission sets, and the solution to this utility maximization problem is now 1/3. So there's no other choice, basically. Node A and B communicate at 1 bit per second. They get 1/3 of the time. And similarly, node A and C and B and C. And so here's where it gets a bit interesting. So in the first concurrent transmission set, node C jams, but since A and B are communicating at 1 bit per second, no packets are lost. And here, the attacker, node C, opts to cooperate with the protocol. And the question is, should it cooperate? Why doesn't it jam? Because if node C jams, then those concurrent transmission sets will be removed from the feasible set. And then node C will not be represented in the feasible set of concurrent transmission set. So the effective rate for the future will be 1 bit per second, which is larger than 1/3. So basically, if node C jams, then it reveals its hand. It basically reveals that it's an attacker. So it does more damage by opting to cooperate with the protocol. So in general, the attacker effectively has two strategies. It can either jam to disable concurrent transmission sets, or it can cooperate. In steady state, so after a large number of rounds, this rate loss is amortized effectively. And the key argument is that only a finite number of rounds can be disrupted, because there's only a finite number of concurrent transmission sets. And the effective minimum rate over the whole operating lifetime is 1/3 bit. So if you recall, the first round failed, the second round failed, but if we have 1,000 rounds, the rate loss caused by those failed rounds is basically negligible. And moreover, there's only a finite number of rounds that can fail. So if we choose a large number of rounds, then we can say that the rate loss because of failed rounds is negligible. And so now I have a question for you. What happens if a bad node defers disabling a concurrent transmission set? What if it defers disabling a round? Perhaps to build trust in the network. What effect does that have on the performance of the network? So here I'm showing you what happens if node C, if the attacker opts to disable a concurrent transmission set in the second last round. Until it disables that concurrent transmission set, the network, the utility is actually much higher than 1/3. The minimum rate is 1/2. So an attacker actually has no incentive whatsoever to delay disrupting an attack. Because if it does so, it actually only improves the performance of the network. Okay. And here's something that I'd like to point out. So in each round, the network solves this utility. The network attempts to maximize this utility, but it's over the pairs of nodes that cooperate. And the key point is that we don't know which nodes are bad. We don't know which nodes are bad. So how do we know which nodes are cooperating? How do we determine which nodes are cooperating? So our operating assumption is that if a node is represented in the feasible concurrent transmission set, it's cooperating. But this assumption is not necessarily true. You know, a bad node might be jamming. But the argument, the important argument is that this assumption is false at most only a finite number of times. It's the key argument. And we amortize the loss. So every time this assumption is false, that might result in a failed concurrent transmission set. But that can only happen a finite number of times, so we can only lose a finite number of rounds. And we choose a large number of rounds to amortize that rate loss. So in the example that I showed you, the utility that's nearly achieved, and the reason I say it's nearly achieved is because we have a few rounds are lost, so we can get within epsilon, we can get arbitrarily close to this utility. And you'll notice that this expression is greater than or equal to the min-max expression. So here, theta represents the disabled concurrent transmission sets. And and that's why the achieved utility is this min-max expression. Okay. So I showed you how the protocol works for a very simple, like, 3-node network. And now I'm going to try and briefly explain to you how this protocol generalizes to, networks that are not just 3 nodes. So in the neighbor discovery phase, there's nothing really fundamentally different. But in the network discovery phase, that's where things get a bit more interesting because you need to build the good nodes need to somehow establish a common view of the network topology. And so that's where the Byzantine general algorithm comes into play. And moreover, a common view, just because they have a common view of the network topology and a common view of all the link parameters, that doesn't necessarily mean that that view is internally consistent. And so what I mean, so here's an example to try and illustrate the point. So here we have a simple 4-node network where A, B, and C are good and D is bad. And node A and C don't have a direct connection. So as a result, if node A wants to estimate perhaps node C's clock or some information about node C, it has to rely on the information provided by either node B or node D. And of course, it doesn't know whether these nodes are good or not. So if both estimates, if the estimates from both paths are the same, then we have no problem. But what happens when those estimates differ? In that case, node A has to determine which of these paths is actually accurate. And in practice, what happens is that this attacker node D introduces some fundamental uncertainty into node A's estimate of node C. And if we want to reduce that uncertainty, we need more overhead. That's essentially the trade-off that happens. Okay. Oops. And so this problem can get a lot more, complex, I guess, in general networks. So here I have node A and C, and there's one good path, but there's lots and lots of bad paths. And the estimates, node A's view of node C might be different depending on the path. So, and finally, in general networks, bad nodes can simultaneously jam and cooperate. And here's an example of how that happens. So here we have two bad nodes, nodes C and node D, and two good nodes. And What node C can do is jam, and since the two attackers have full cooperative capabilities, since they are, since they are able to fully cooperate, node D can claim that all of the node C's packets were received while node C was jamming, in an attempt to disrupt the link over here. So as a result, the achievable, so when I apply this protocol to general, when you apply this protocol to general networks, that's why when we look at the strategies of a bad node, it's capable of both jamming and cooperating simultaneously in a concurrent transmission set. Okay, I guess I have maybe a few more minutes left. So in conclusion, I'm going to try and explain to you why it's really difficult to achieve, the big upper bound, the upper bound over all, where the rate is over the information theoretic capacity region. So the question I'm asking you is whether this protocol, whether the protocol suite that I've that I've gone through, whether I can modify it to include, to go beyond just simply time-sharing concurrent transmission sets. Because, well, in the information theoretic community, we have lots of other techniques just beyond simple time-sharing. We have, dirty paper coding, superposition coding, all kinds of other, complex coding schemes. And is it possible to incorporate all of, that insight into this result? So the problem, of course, is that we don't know what the information theoretic capacity region is. It's unknown, and it's unlikely to be characterized anytime soon. But I argue that this problem is not insurmountable. And what do I mean by that? Well, I'm saying that we don't need to characterize the information theoretic capacity region to try and go for this upper bound. Because by definition, if a rate vector is in the information theoretic capacity region, there must be some achievable coding scheme for it. And so I can assume that that protocol uses that coding scheme even if it hasn't been discovered yet, or if we don't know it yet. But there's another problem, I think, that is a lot more difficult, and that is the fact that this min-max essentially implies that the network has a priori knowledge of what the attackers will do, whether an attacker will jam or cooperate. And in the example, when we restrict ourselves to just simply time-sharing concurrent transmission sets, the achievable utility works out. It's a special case in which it works out in that way where we have a saddle point. Min-max is max-min. But in general, we don't have that saddle point. We don't have this result. We don't have that property. So I think actually this problem is really where the bottleneck lies. And here I try to, I'm basically describing kind of a failed attempt. I don't know if I have time, but a failed attempt to try and hit the upper bound. But maybe I'll skip that, I guess. What are some of the additional issues, I guess, that we need to go over that need to be addressed, I guess, with this kind of work? So, if we want to generalize this result, for example, to information theory, to include information theoretic techniques, All of our rounds are finite length, so so all of the coding schemes would be over finite block lengths. And hence, there will be some probability of error associated with whether a packet is received or not. And in our model, we assume that either a packet arrives or it doesn't. We didn't really include this probabilistic mechanism. So more work kind of needs to be done. So in conclusion, what we proposed was a model-based approach to secure protocol design, in which we have a protocol that takes a collection of nodes, some of which are good and some of which are bad, from a primordial birth to a fully functioning network. And we have a protocol suite that is nearly utility optimal in the min-max sense over concurrent transmission sets, and that it's immune to all possible attacks that satisfy this network model. And so some extensions, as I mentioned earlier, are trying to incorporate the techniques of information theory, probabilistic receptions, also mobility. So in our network model, everything is kind of static. And there's other questions as well as to what type of utility function is best, for the situation where you have good nodes and bad nodes. And also the transient performance. So in the example that I showed you, we went brute force through every feasible concurrent transmission set. But perhaps that can be improved. And these results are really meant to be kind of an existence proof to show you that a protocol does exist, and perhaps to inspire other ways, I guess, of designing secure wireless protocols. All right, thank you.